Okay, then shall we start?
Yeah.
So thank you for attending the second day of the IBS ICTP workshop. Today we have two speakers, Dr. Joshua Abbey and Dr. Pierluca Carenza, talking about astrophysical implications of axions. The first speaker is Dr. Joshua Abbey from Kabuli IPMU, University of Tokyo, and he will give a talk on the terrestrial signals from axion star explosions. Then Joshua, please start.
Firstly, I want to thank the organizers for organizing this nice workshop and for the invitation to speak. Today, I would like to tell you about a potential new signal that can be searched for in existing or near future axion dark matter experiments coming from transient bursts of relativistic axions with a focus on the specific case of axion star collapse and explosion. I'll explain how this works as we go along. Oops. Okay, so let me start with a brief review of some aspects of axion physics. We've already had a number of interesting reviews yesterday about the QCD axion and how it solves the strong CP problem, and more generally how ALPs can be well-motivated dark matter candidates and searched for with NASDAQ and so on. For my purposes, I will characterize axion fields by basically two input parameters. First, there's a low scale M, which is the particle mass, which is, for me, always constrained to be lighter than an EV, because what I'm concerned with is the wave-like dark matter. So dark matter that behaves as a classically oscillating field rather than individual particles. In order for this particle to be dark matter, it needs to lie within a finite range, cut off at the low end by, in the minimal case, you require that the particle mass of dark matter is not so small that the dark matter particles cannot fit inside of dwarf galaxies. So when the particle mass is as low as 10 to the minus 22 EV, then the Compton wavelength of these axions actually is larger than the size of the smallest dwarf galaxies, and therefore they can't really account for the dark matter in those galaxies. And there are stronger constraints on the axion mass coming from Lyman alpha observations, from observations of rotation curves in the centers of disk galaxies and so on. But that's basically the range in mass. It's a very wide range in mass. And then the second parameter I'm concerned with is the axion decay constant, which does two things in general. Firstly, it generally suppresses the couplings to matter, and I'll talk about that in a second. So couplings to matter generally go like 1 over this decay constant F, which is a large scale, at least 10 to the 9 GeV in order to be consistent with astrophysics. But it also does a second thing, which is that the axion decay constant characterizes the axion self-interaction potential as well. So on the right, I've given two examples of axion or ALP self-interaction potentials. They're actually fairly similar in form because they generally preserve an approximate shift symmetry on the axion field when phi goes to phi plus f, phi plus 2 pi f, sorry. 2 pi phi equals f, sorry. So anyway, for the QCD axion, you have this chiral potential, which depends on the ratio of quark masses, MD over MU, which is Z. But in general, for ALPs, you generally find something like this 1 minus cosine potential, which is slightly simpler. And if you expand these potentials, you get, at least to leading orders, things that are qualitatively similar. For example, the leading self-interaction is attractive. In this talk, I will be concerned especially with what happens in axion theories when the decay constant is large. And there are a couple of reasons why you might be interested in this model space. Firstly, as I've illustrated in the figure on the left, I've kind of cherry-picked a few models to illustrate this point. Large decay constants actually are not disfavored in terms of theory. There are many theories that actually generically lie at decay constants larger than the Gutt scale and even approaching the Planck scale. And if you take seriously the predictions of a string axiverse, which is to say, if you have some high scale theory like string theory with many compactifications giving rise to lots of broken global symmetries, you generally expect a plethora of axions populating both mass and decay constant space. And very often these will lie at large decay constants because that's the scale of this sort of quantum gravity theory. In a more phenomenological way, axion stars with large decay constants have been interesting to people. One reason is because when axion stars are formed with decay constants close to the Planck scale, they are expected to have properties similar to neutron stars in terms of size and mass, and therefore in spiral and merger of axion stars and neutron stars can give rise to multi-messenger signals, including gravitational waves that people have investigated. And finally, when you have axion stars collapsing with large decay constants, it has been suggested that these things can form black holes directly, which is not the generic thing for axion stars to do. I'll explain what axion stars typically do, but if this claim is true, then you could explain, for example, intermediate mass black holes in sort of unusual mass ranges, which may have been observed recently, by the way, at few solar mass. By the way, for future reference, I will just mark this point on the QCD axion line, which I'll just call M5 and F12, so that we can give some numerical estimations a little bit later because this space is fairly broad. Although the case of large decay constants is theoretically motivated, it's actually very hard to probe for the reason that I already told you. Couplings to the standard model are suppressed as 1/f. So just as an example, here is a recent paper which summarized the current and likely near future reach of many experiments going on around the world for their sensitivity to axion couplings to photons. So the dark curves here are the current constraints at the top coming from nuclear physics, from astrophysics, I'm sorry. And the blue curves that are sort of cutting down in a fairly narrow way are the haloscope searches. And then all of these shaded regions are the possible future probes, sort of in the long term, where can all these proposals kind of reach? And you see that even in the most extreme case, we're like barely pushing decay constants of order the gut scale, and really, almost never any higher than that. So is this the best we can do? Well, if you want to do better, you might try to take a slightly different approach. Rather than pushing down from the top of this curve, you might try to look for different kinds of systems where the fact that the decay constant is large actually improves your signal rather than diminishes it. So a good example of this is axion black hole superradiance. If you don't know the story, just very briefly, when you have a rapidly rotating black hole in the presence of a scalar field like an axion with a very low mass, in some range you can have runaway production of these axions in L not equal 0 states. And what this does is it spins down the rapidly rotating black hole as it sort of produces axions out of the vacuum. So what this means is that if you observe a rapidly rotating black hole, it means that this process has not occurred, and therefore those axions must not be around. So that's a really kind of cool way to set a limit. It's especially interesting for us here because this process is only efficient when the decay constant is sufficiently large, because if the self-interactions of axions are too strong, which is to say, if F is too small, then these clouds of rotating axions cannot form very large masses. They eventually collapse. So they fail to ring down the black hole, and you kind of lose your constraint. So superradiance limits generally push up from the bottom of the curve of the plot rather than coming down from the top. So we like to ask, are there other systems where something like this might be true, where you actually have a gain from having a large decay constant? A second motivation for our work is that suppose we discover an axion in one of these axion dark matter experiments like ADMX. How will we know that it is a QCD axion rather than an ALP? How will we know, how can we probe properties of the axion potential? And it turns out that this is extremely, extremely hard because what we're measuring in Axion cold dark matter experiments are the oscillations of the Axion field around the bottom of the potential, basically m squared phi squared. And you could have lots of different Axion theories that have the same leading order oscillating behavior around this minimum, but very different structure of the global potential. But the deviations from harmonicity are generally suppressed by 1/f squared, which, for the QCD Axion is 10 to the minus 37. But for other kinds of ALPs, this can be much, much smaller still. So it's unlikely that these kinds of self-interaction terms will be probed in conventional dark matter experiments, at least for the kinds of searches we're used to thinking about. So we also would like to ask, is there a way to try to probe these self-interactions? So with that, let me just give you a brief overview of what we'll talk about today. So I've just given you some of the background and motivation for the work. In what follows, I will explain to you what Axion stars are and what happens at large decay constants in a quantitative way. And then I will tell you about Axion star explosions and other possible bursts of axions, and then explain what's coming next. Okay, so take a look at this figure. So this is actually this is a movie if you go to YouTube. It's a snippet of a simulation from an ultralight dark matter simulation. And this is actually sort of a simulation of an entire galaxy, but you can imagine it kind of even on a smaller scale, depending on the sort of size of your Axion field, but let's just take it for what it is. What you see in this picture are lots of fluctuations of the dark matter field with size of order the de Broglie wavelength of the Axion. This is generically what you find for light scalar fields. This is kind of the wavy nature of light scalar or Axion dark matter. I'd like to call your attention to what appears to form in the center of these simulations, which is an Axion star. So generically in these simulations, they start from cosmological perturbations and they watch large scale structure form and all of this kind of stuff. And by the end, they find a very large chord profile in the center of their galaxies, which is what we call an Axion star. And this isn't just found in cosmological simulations now, although they were the first to find it in a simulation. There are now a number of different groups doing simulations on widely different scales for different Axion theories, finding basically the same thing, that what Axion field likes to do is form these clumps that I'm calling Axion stars. So on the left is the cosmological simulation I showed you. Here's a second one by Mops et al., another cosmological simulation. This simulation of Levkov, Panin, and Kachev used basically white noise initial conditions and basically found that Axion stars will form in such a case. And on the right-hand side is a simulation inside of an Axion mini cluster forming an Axion star within this kind of dense cloud of Axions. What is really cool is that all of these different, the structures formed on all of these different scales and all of these different simulations is the same object. It is, an Axion star is the ground state configuration of a large number of Axion particles. And in spite of the different initial conditions and different assumptions in these simulations, they find the same object forming all the time. So Axion stars appear to be a generic prediction of many, many Axion and ALP theories. Let's dig into this a little bit deeper. And to do that, we'll turn to the equations of motion for the Axion field. So because Axion dark matter is non-relativistic, and because the particle mass is so low, the occupation number is very high, so it should behave as a non-relativistic classical field that basically oscillates with a frequency very close to the particle mass. So what one generally does is start from a Klein-Gordon field phi and expand it in terms of a rapidly oscillating phase, e to the IMT, times a non-relativistic wave function psi, plus the complex conjugate, because this is a real scalar field. And in the non-relativistic limit, the Klein-Gordon equation reduces to the Gross-Pitievsky equation coupled to Poisson gravity. So this is what I've written here. So on the left-hand side, we have the remaining time dependence of the non-relativistic field, which is, by assumption, very small. There's a kinetic energy term, of course. This is coupled to Poisson gravity, so just non-relativistic Newtonian gravity. And this is the self-interaction potential. So for the 1 minus cosine potential, as I told you, this gives you an attractive leading term, but then a repulsive next to leading order term, and so on. But all of these can, in principle, contribute. And what is an axion star? An axion star is the ground state of these equations of motion at fixed mass, or at fixed particle number, if you like. So it's fairly easy. So firstly, it's fairly easy to solve these equations directly. You know, if you write 3 lines of Mathematica code, you can basically have your very own axion star solutions, and that's what's given here on the left. These are the rescaled axion star wave functions for 3 different choices of central density. You see that the states with the lowest central density generally have the largest radii, and vice versa. But you can see, just by balancing the basic forces at play here, you can arrive at the basic properties of axion stars. For example, if you look at the lowest density configurations, then you can effectively neglect the self-interaction potentials, because those are suppressed by higher powers of 1 over r. And then you can balance the repulsive kinetic energy against the attractive gravitational energy, and you arrive at what's known as a dilute boson star. And the parameters are basically given here. So these things for QCD axions are generally, you know, very far from a solar mass, let's say that. But for other kinds of ALPs, you know, they can be much more massive or much larger, and so on. So these are called dilute boson stars, or dilute axion stars. If you continue increasing the density in this calculation, you eventually turn on the leading attractive self-interaction of the axion. And if you do that, then there is some density at which that self-interaction turns on. And when it does, it actually triggers an instability in the star. So if you start from an axion star that is on the so-called dilute branch of solutions, where r goes like 1 over m, at some point, the density becomes such that the self-interaction turns on. So this is the critical point, which has a calculable max critical mass and radius. And then the solutions turn over onto a second branch that's sometimes called the transition branch. This is because these are unstable under perturbations. So on the second branch, the states are unlikely to have cosmological significance. So what would really happen is, if you started from one of these states and it increased in mass, it would grow and grow and grow along this curve, and then hit the critical mass and then collapse. And I will tell you in a little bit later what happens when it collapses. If you want to go to higher densities, it turns out that this formalism is ineffective, because we have assumed from the get-go that these are non-relativistic states. But if you continue to increase the density too much, you eventually arrive at configurations where phi is of order f. And this means that higher orders in the self-interaction potential contribute. And you also have back reaction on the non-relativistic modes. So you actually need a relativistic theory to compute properties of these states at large densities. So I'm going to explain to you fairly briefly a brief overview of many years of work developing a formalism that sort of takes all this into account. Our work is based on one of the earliest papers on boson stars by Ruffini and Bonazzola in 1969. And what they did was they started from the full UV theory, the Einstein and Klein-Gordon equations, where the Klein-Gordon equation is treated as a quantum equation. So where phi is the quantum field. They suggested that, of course, you can expand the quantum scalar field in powers of the creation and annihilation operator. So they said that this should be linear in creation and annihilation operators with quantum numbers NLM times some wave function with quantum numbers NL times spherical harmonics and an oscillatory phase. So this is almost fully generic. And their insight was really just to reduce this to merely the ground state contributions in spherical symmetry, which would be relevant for an object like a boson star, where these things are maximally cold. It has to be the ground state of the equations of motion. And because it's the ground state, it's also spherically symmetric. So their field operator reduced to something very simple, and starting from the quantum Klein-Gordon equation, they took an expectation value in these n particle states given this operator, and they arrived at a simple equation of motion for this single wave function R. In the case that they considered, which was the case of no self-interactions, their result is an exact solution. And actually, this has been replicated many times in many different ways. So that was kind of what they got, although they were one of the first. On the other hand, so you treat the Klein-Gordon equation as quantum, but you cannot treat the Einstein equations as quantum. So of course, again, you need to take expectation values of T mu nu. And when you do this, you arrive at expectation values like n 5 squared n, which gives rise to basically powers of R like R squared. So every phi gives you an R squared, and every n gives you an n, and so on. That's basically their formalism. What we thought to do back in 2014 was to start from their formalism and go explicitly to the non-relativistic limit and see what you get. So, and in doing this, we actually wanted to include self-interactions so that we could study something like Axion stars, which have attractive self-interactions. So we took two approximations. Firstly, we assumed weak binding in the star, which is equivalent to the non-relativistic limit. The eigenenergy of the non-relativistic mode mu should never be far from m, which is to say mu minus m should be much less than m, which we parameterize by something we call delta, 1 minus mu naught squared over m squared. It should always be much less than 1. And we rescaled our parameters accordingly. The other assumption here is weak gravity. So you start from these metric functions a and b appearing in the Einstein equations, and you expand them in a small parameter delta, which is what appears on the right-hand side of the Einstein equations. 8 pi g f squared should always be much less than 1. And if you do this and you start from the Ruffini-Bonazzoli equations, you arrive at a even simpler set of equations, although they appear at a somewhat less familiar form, I think, than what you may be used to. But we showed, of course, that these equations, although explicitly derived from the expectation values in the relativistic case, are exactly equivalent to the Gross-Pitievsky-Poisson equations that are usually just considered to be the starting point. So this allowed us to make connection with the usual theory. And you find that if you solve these equations of motion and these equations of motion, you arrive at precisely the same solutions. So this is what is shown here, where the dashed lines are solutions of the Gross-Pitievsky-Poisson equations, and the solid lines are solutions of the Ruffini-Bonazzoli equations. And so you get exact confirmation. But our formalism allows you to go a bit further. So, firstly, I'll remind you that there's a one-to-one relationship between the density, R parameter delta, which characterizes the deviation from the non-relativistic limit, the mass and the radius of the object, and so on. So what our study suggested was that the critical mass that had appeared in other places, with other formalisms before, that critical mass corresponded to a particular value of delta, which is about 8.6 f over m Planck. And this was our first indication that something funny is going to happen when f approaches m Planck, because delta is by definition, I'll show you again, delta is by definition less than 1. It's 1 minus something squared. So it must be, if it's real, it must be less than 1. So some part of this theory must break down if f approaches m Planck. That was our first indication. If you want to go beyond the non-relativistic limit, which was one of our motivations, you can actually further extend the Ruffini-Bonazzoli equations. This is necessary because this ansatz is not exact, firstly, in an interacting theory. When you go to high density, the field values can be of order F, meaning that the self-interactions can become strong and you get large relativistic corrections. So our resolution was to generalize the Ruffini-Bonazola ansatz to include contributions from non-linear order in creation and annihilation operators. So including, for example, A cubed, which can contribute from back reaction of higher energy modes onto the low energy modes. So you can think basically of our formalism as integrating out modes of 2 mu, 3 mu, 4 mu, and calculating their back reaction on the non-relativistic mode of eigenenergy mu. And we can do this as a power series in delta, which is basically telling us the deviation from the non-relativistic limit. So we're able to kind of control this as a perturbative series. Reminding you what happened in the Ruffini-Bonazola case, you start from the quantum Klein-Gordon equation, you take this expectation value, which is the only non-zero one when you have a non-interacting theory. You arrive at this simple non-relativistic equation, and you take these two limits, and this is what you get. For the generalized Ruffini-Bonazola, there are higher order expectation values you can take that are generically non-zero, because now you have higher order creation and annihilation operators. So when you do this, you end up with, in general, k infinitely many equations, basically, for each mode k, and generically they're non-zero. So it's an infinite set of equations, but because of this perturbative nature, we can cut it off at some power of delta, and it remains calculable. So for Axion stars, and I'm going to drop the gravity term for now just to kind of show you how this goes. So if you start from the first non-zero expectation value, n to n minus 1, add order delta to the fifth. So this is the basically leading order GRB correction. This is what you get. So you end up with a mass term, a kinetic term, a self-interaction term, which is what you found in the original Ruffini-Bonazola case. Our calculation includes the higher order self-interaction term coming from phi to the 6th, right? So this was the next self-interaction term, but it also includes a back reaction of the mode with 3 mu on the equation of motion for the mode of energy mu. So this is basically a back reaction term coming from integrating out something like three axions coming in, back reacting on a single bound axion. And at this order in delta, those are the only corrections. The second GRB equation, which is relevant for Y3, gives you something like this. But again, if you cut it off at delta to the fifth, then you end up with finitely many terms. And the third equation actually only couples at higher order in delta, so it never contributes. If you include all of these contributions, what you arrive at is a mass spectrum that is very different from what you would have gotten just solving the Gross-Pitievsky equations, which others have done in the past, and we wanted to clarify. So if you just solve the non-relativistic equations in a region where they are not applicable, you would find something like the dashed line. And if you instead solve the GRB equations at order delta to the fifth, as we did, you find this curve instead. So two things are different. Firstly, the position of the minimum mass is shifted, so this curve turns over sooner, but also there's a cutoff corresponding to some large value of delta at which the perturbative expansion becomes unstable. Here we chose delta of 0.7, but basically there will be some cutoff in delta. So also a generic prediction of our formalism is that you can't predict these dense states to arbitrarily large mass, because basically your calculation breaks down. So if there are states at larger m, we don't know about it. One last little bit of table setting. All of this will lead into the signals, of course, but Axion stars are, so what do I want to say? So generically, axions are real scalar fields. So there's no symmetry protecting axions from number changing operations. So for example, axions can decay to photons. We know that this is possible, but the decay rate is very slow. And this is not captured by any of the physics that I've described to you before, because all of this was happening at fixed n, right? So we would like to include contributions corresponding to number changing operations. So what does this look like? Well, if there are number changing interactions inside the star, what it will do is it must, because the initial states are non-relativistic, it must give rise to axions that are emitted from the star. They must come out with very high energy, and this would not have been included in our field operator. So we've only so far included states where mu is smaller than m, and the full theory should include states with some omega that can be larger than m. So this we did too. So here on the left, we have the GRB operator corresponding to the bound states. And we also included scattering states where, at linear order, the scattering state should be a spherical wave. So it can be approximated this way. Using this formalism, you can calculate decay processes by taking off-diagonal matrix elements of the self-interaction potential. So you find interactions of this form, for example, as one of the leading ones. So you can have 3 non-relativistic axions that are bound in the star coming in and annihilating to a single axion that is emitted from the star with a roughly calculable momentum and energy. And you can calculate the total decay rate by taking this matrix element and using Fermi's golden rule and so on. So it gives you kind of a particle physics handle on these decay processes. Right, so the decay to photons, of course, is super slow. So what happens with these decay through self-interactions? Some of these decay processes, by the way, are only possible because the axion star is bound, which means that these initial states are not quite momentum eigenstates. Although the momentum is peaked near 0, they do have a momentum distribution just because of the Heisenberg uncertainty principle. They live in a bound state of size r, so the momentum uncertainty can't be smaller than 1 over r, 1 over big R. So if you calculate the decay lifetime of these objects, you find this exponential dependence on the parameter delta, which means that these states are exponentially stable unless delta is large, which is to say, unless you start to deviate from the non-relativistic limit. If you translate this into the plot that I showed you before, then you see that all of these states are unstable to decay. So some of the densest states on this transition branch are unstable, and then the whole of the dense branch is also unstable to decay processes. Okay, approaching the Planck scale, we had a couple of hints that something funny was going to happen as you start to do the calculation at larger and larger f. The first one I already told you. This naive critical mass calculation implies that delta will exceed 1 when f approaches m Planck. That can't be right. Secondly, in this kind of global picture of the axion star mass radius relation, this critical mass and this minimum mass here on the left will approach each other as a function of f, and they will actually, if you just naively assume that they retain their values as you increase f, you find that they will coincide when f over m Planck is about 1 over 40 or 10 to the 17 GeV. So again, something must break down in the calculation by that point, because otherwise you would predict that the maximum mass is smaller than the minimum mass. Right. So we did the full calculation, including the next to leading order in these relativistic equations and the decay processes, and this is what we found. So these are the usual mass radius relations on the dilute, transition, and now dense branches of axion stars. And you see that as the decay constant increases, as predicted, the critical points sort of come closer and closer to each other. But around 10 to the 17 GeV, some funny things happen. So the shape of the curves firstly starts to change. But more importantly, this decay process starts to become more and more relevant even on the dilute branch of axion stars. So where before these dilute states were sufficiently dilute that these decay processes never applied, now when f is large, in fact larger than about 10 to the 17 GeV, the decay processes actually are fast enough to to deplete any excess mass that the Axion star has. So this is contra previous claims that, at large F, dilute Axion stars continue to be stable. So you can also see on the right figure here that as a function of F here, or our parameter delta, above about 10 to the 17 GeV, the decay instability is stronger than the gravitational instability for the Axion star, which is to say states on the dilute branch of Axion stars become unstable. So that's a key result there. So now finally, let me tell you what happens when Axion stars collapse. So I've told you about all the pieces of this sort of picture. So now let me imagine that I have a stable Axion star on the dilute branch, and I let it evolve in the galaxy. So by the way, I should point out that this basic process was worked out in a paper by us in 2016, and very excitingly to us, our prediction of what happened to a collapsing Axion star was quickly confirmed by simulation. So what happens to a stable Axion star? So you can imagine that it firstly can grow in mass. So either through accretion of background axions, or if you have many mergers of Axion stars that give rise to more and more massive states, these stars will shrink in size as they grow in mass until they reach this critical point. And at that point, they will collapse. Because these states are so non-relativistic, the initial gravitational collapse is very smooth and strictly symmetric. So you can basically calculate it in the non-relativistic limit without any problem until it reaches a certain point when the density is sufficiently large and some of these number changing transitions turn on. And what happens is that the star basically explodes in what is now called a bosonova explosion, like a supernova, but of bosons. And in this process, it was found in the simulation, a large fraction of the energy in the star can be emitted in relativistic axions that escape the star. So an order 1 fraction of this critical mass can be very large, depending on the ALP. It can be a very high, large amount of astrophysical energy being pumped into relativistic axions that just stream through the galaxy. So that's the signal we would like to look for. What happens after the explosion is a little more speculative. An order 1 fraction of the mass remains non-relativistic and gravitationally bound, but not in its ground state. So it may be that it finally forms a new Axion star, but that's not actually known. So to get to our signal, let me tell you a bit about what the simulation found, because we use this as input for our study. So firstly, what did the simulation do? They use the full relativistic equations of motion to simulate the Axion star collapse. And in these final moments, they see rapid transition from non-relativistic particles to relativistic particles that escape from the star in this explosion. And the explosions are what you see as these very sharp, wiggly lines in this figure. So on the left side here, what you see, so this is the density as a function of time. The density is increasing smoothly as it collapses until it reaches a certain point, and then, everything breaks loose. You have lots of number chain transitions, much like a supernova. It's a very messy environment where lots of axions are being emitted, but for a very short amount of time. So there's this kind of crazy period until it settles for a minute, collapses again, and then explodes again and again and again. So you can actually have many, an order few number of explosions before enough energy has left the star that it can basically settle in a low density environment that does not further collapse. For us, it'll be important to note that the duration of these bursts is fairly short. So only a few hundred, like 1/m cycles for this explosion, for each explosion. Secondly, and importantly, what the simulation found was they were able to calculate the emission spectrum of the outgoing axions. So this is dEdk normalized, appropriately as a function of k/m. So what you see is a large buildup of axions at small k, corresponding to the non-relativistic component that stays kind of bound. And then you have this peak structure in the relativistic side. So the first relativistic peak corresponds to momenta of order 2.5 in units of m. And the spread in this momentum distribution is of order 1 in units of m. But even in this first peak, you can have a very large amount of energy emitted. So if you just do the math, for a QCD type axion, this is 10 to the 41 GeV, which is, again, 10 to the minus 14 or 15 solar mass, something like that. Potentially detectable if this were to happen nearby to Earth. But we want to do a more thorough study than that. So I will point out that in our study, we ignored a couple of things for simplicity. So firstly, we ignored the fact that there are multiple explosions, but we think that this probably only strengthens our case. If there are more similar explosions that are kind of landing very near each other, you could actually use this to distinguish our signal from some other transient source. We also included only the first relativistic peak. We didn't include these higher order peaks, which in principle would show up in some of the same experiments. But to make our signal estimation simpler, we only included the first peak for now. So these are things we can talk about for future work. Okay, so here's the basic picture. So again, you have an axion star, it grows in mass somehow until it collapses and there's a Bose-nova. And now imagine that this happens a distance r from the Earth. So suppose you have an experiment, a telescope over here somewhere, and it's a distance r. Naively, what do you expect the energy density to be at the position of your experiment? Because you might expect that you need a large energy density to be detectable. So just a simple estimation, you start from the energy integrated over the peak that I showed you in the last slide, divided by basically the volume element in this burst. So there's a 1 over r squared dilution of the signal just based on spherical wave spreading. If the thing is a distance r away, you lose signal by r squared, times the duration of the burst, because the energy density will also be spread over this short burst duration. And this gives you an energy density that's about 6 or 7, about 7 orders of magnitude larger than the background dark matter field for QCD axion inputs and for a pretty nearby explosion. So in principle, you can have a much improved energy density. However, the downside of relativistic particles is that unlike axion dark matter experiments, which generally they gain from the coherence of the axion field, right? An axion dark matter experiment can integrate over 10 to the 6 oscillations of the axion dark matter in order to build up a signal. But naively, you would expect that our signal, which is relativistic, will just be a set of incoherent waves, totally poor quality oscillator. And so you will build up signal much less effectively. So naively, you might guess that our signal can only win if this product of ratios is smaller than 1. So if we gain in density more than we lose in quality factor, then potentially we can win. This is roughly the scaling suggested by Hitoshi Murayama and friends, talking about relativistic axion signals from cosmological sources. What we found, though, is that for transient signals, these estimations actually break down, and I'm going to explain to you why. So firstly, let me tell you why they break down in a way that's negative to us. So I told you that the energy density will be diluted by the duration of the burst, right? But the duration of the burst actually changes as the axions are in flight, because basically the fastest axions, even though they're only a little bit faster than the slowest axions, because they're all relativistic, they will still arrive at the detector sooner than the slowest axions. So actually you get an overall wave spreading of the burst, so that even if you have a very narrow burst at the source, you can end up with a very shallow, wide burst at the position of the detector. So that means the instantaneous energy density will be much less. So rather than the energy density being diminished by 1 over r squared times some narrow burst, you actually can have a situation where the energy density is diluted as 1 over r cubed, which is very unfortunate. because r is astrophysically long distances. However, not all is lost, because even though the duration of the burst the duration of the burst increases even as the energy density decreases. So as long as the burst never becomes too wide, such that you can't run your experiment long enough, you can still catch the whole signal, and actually you regain that same factor of R that you were thought to have lost. So this puts a constraint that you need for the burst duration to be less than some experimental timescale, let's say about a year. But this turns out not to be a problem, and I'll show you the figures in a second. So good. So we're back to kind of square one. So maybe the wave spreading is not hurting us, but actually it even helps us, because unlike this incoherent wave story, it is advantageous that the momentum modes themselves spread in flight. So because the fastest axions arrive to the detector soonest and the slowest arrive the latest, at any given moment in the detector, you actually have a very narrow distribution of momenta. And when you have a very narrow distribution of momenta, you can integrate the energy very efficiently. So what you will see in the detector is fairly separated narrow momentum modes arriving at the detector in succession, the highest energy arriving first. So this effectively gives you a kind of coherence of the signal in the detector, such that you actually can regain some coherence that you were thought to have lost. So this was a key insight that we discovered that actually allowed the signal to be detectable. So how do we search? I know that I'm running out of time, but I am almost done. So firstly, we wanted to ask, we compute the real sensitivity ratio, so not the naive one that I showed you before. So the real sensitivity ratio is a complicated function of all of these timescales that I won't explain in detail. But basically, this integration timescale is the experimental, which we assume to be about a year. There's the coherence time of dark matter. There's the burst duration, after wave spreading, and there's the coherence time, the effective coherence time at the position of the detector. And we want to ask, is a given dark matter experiment at least as sensitive to these relativistic bursts compared to a cold dark matter burst, which is to say, can this ratio be less than 1? And then in order to compute the absolute sensitivity, we needed an experimental benchmark. So we used the Abracadabra long-term reach curve from 2016. Of course, we're aware that this is an old figure, and we're also aware that in recent years, Abracadabra seems to be merging with DM radio. So it's not clear exactly where the sensitivity is expected to lie, but we needed a benchmark, so this was the one we chose. What's nice about Abracadabra is that they have the potential to run in a broadband search mode, which is what we would need for the signal, because at the end of the day, the signal will be very broad in mass. The second thing we needed to check was that the number of bursts that are happening nearby to the Earth will be enough that you expect to see one roughly in an experimental lifetime. So this depends on a lot of complicated cosmology that we didn't go into in the paper. Some of these numbers are sort of put in by hand because no one really knows the mass distribution of Axion stars, or how quickly they accrete mass, or how frequently you expect them to collapse. So we wanted to make an estimate for the number of collapsing Axion stars in our vicinity, but you should take these numbers as being very rough and not too seriously. Okay, so this brings me to our main result. Let me walk you through this figure. So firstly, this is 1 over F and M at the top of the curve, and here you have in green the experimental constraints on axions. At the bottom of the curve, you have a region where there are no Bose-Novi. This corresponds to the first half of the talk when I explained to you that dilute axion stars won't collapse and Bose-Nova if the decay constant is sufficiently large. So we're constrained to the region between the green curve and this gray curve. So the blue regions are the potential experimental reach regions for Abracadabra. What is cool about this is that the reach is vertical in F. This is because although the coupling decreases as 1/f, the coupling to photons, our signal grows as the square root of the energy output, which is proportional to F. So the product of the explosion size times the coupling is independent of F, and you end up with these vertical contours. So you see that we would be sensitive to Axion star bursts out to a distance of about 10 parsecs. So sort of starting to reach astrophysically large sizes. Yeah, secondly, I've told you, Axion stars can collapse down here. Thirdly, there are some contours corresponding to a frequent number of explosions. So for explosion lifetime of 10 gig a year, which is fairly arbitrary, we end up with contours like this. So it suggests that these explosions would be a bit too infrequent to detect, but again, there's work to be done to make this concrete. And finally, I'll just point out that there are other simulations suggesting Axion stars coupled to photons can convert to photons through parametric resonance during these collapses. So if the photon coupling is sufficiently large, then actually maybe the photon coupling will dominate. So we're not sure if this is a feature or a bug, because this could be a multi-messenger signal, basically. Maybe I'll skip the nucleon coupling, but here basically the problem is that the potential gain for us is that nucleon couplings are proportional to the velocity of the dark matter, because it's a gradient like phi or nabla phi, and our signal is relativistic. So instead of a 10⁻³ suppression, we would have an order 1 factor. So that actually, in principle, gives us an edge over the dark matter experiments. But there aren't really any good proposals for broadband searches for nucleon couplings in these mass ranges. So some new ideas are necessary here. Finally, I just want to say we extended our analysis to general explosions, basically treating the burst energy as a free parameter rather than fixing it to the Axion star case. In that case, what you find is that if you require the signal to noise ratio, I'm sorry, this should be, oh no. Yeah, signal to noise ratio greater than 1, and at least 1 explosion per year. You can be sensitive to different explosion sizes at different distances. So for example, your best reach will be for explosions of size 10⁻11 solar mass at a distance of a parsec. But you can be sensitive to larger explosions at a kiloparsec at almost the same sensitivity scale. And if you combine all of this into a sort of generic reach plot integrated over any kind of burst size at any distance, you arrive at something like this. So anyway, we think there's some open questions here, but maybe I'll leave that for the Q&A. Oh, I should also point out we're hosting a workshop in December. So you can ask me about it after, or you can take a look at the Indico page here. I think it'll be of interest to a lot of the people in the audience today. So in any case, I'll leave you with my conclusions just to say that we think Axion bursts are a cool new signature that's worth exploring. There could be other sources of Axion bursts coming from, for example, astrophysical mergers, or from collapsing super radiance clouds, or things of that nature. And the fact that they can be detectable in existing experiments makes them very cool targets for the future. So thank you very much.
Thank you for the interesting and comprehensive talk. Then let us have a Q&A session. Is there any question from audience? Okay, let me ask first. In this plot, the mass and radius relation plot, what is the reason that there exists some attractive behavior, attractive solution?
In this figure, you're saying?
Yeah, right.
What do you mean attractive solution?
Like the different f along for different f, they follow some same behavior for the low R case. I mean, different solution
hmm.
follow the same line.
Yeah, you mean at the bottom of the curve
yeah.
here. Yeah, so here it's roughly for the following reason. When you're really in the regime of like these dense Axion stars, the field values become of order F, which means that the densities are fixed, basically of order m squared F squared, right? This means that first of all, the slopes are guaranteed to be the same. So m goes like r cubed, right? Secondly, and I think I show here. So of course these axes are scaled in a particular way, right? The masses are rescaled as F squared over m, but that is the same scaling as this minimum mass. So that means that the starting point of all of these curves will be also the same. So both the starting point and the behavior, m goes like r cubed, will be the same. So that means that all of these curves actually have to follow the same line.
I see.
Does that make sense?
Yeah, right. Another question is, okay. Professor Jae-chan Hwang raised a hand, and please ask a question.
Yeah, I have a question about the collapse. When you do the collapse, either in your work or in simulation, did you assume spherical symmetry?
So in our work, we were doing essentially a nearly relativistic, a nearly non-relativistic calculation, just looking at the initial stages of collapse. And in that case, we were looking at a spherically symmetric case. In the simulation, the initial state is spherically symmetric because they start with basically an Axion star at the position of the critical mass, which would be spherically symmetric. And then when they actually do the evolution, they include, I believe they include non-spherical symmetry, at least in the final states, I think.
Yeah,
I would have to check.
I'm asking it because the collapsing phase, the spherical symmetry is unstable in the collapsing phase, especially if we have a rotation. Everything have a rotation. If something is rotating, the angular momentum conservation will build up as it will act as a repulsive force. So that could lead to, the initially spherical symmetry should be, imposed with high precision so that you can have spherical symmetry maintained.
Yes, I agree with what you're saying. So actually, it's interesting. The same simulation group recently had a paper about rotating boson star states, and they looked at their stability basically. And what they found was that very generically, these rotating states will decay to non-rotating states. They found that any state that started with angular momentum would, with a relatively fast lifetime, I don't remember what that lifetime was, they would actually emit particles to infinity until they ended in a spherically symmetric boson star again. So I think that that's a fairly cool result, but it's very new. I think that's their latest simulation.
Yeah, sounds like it's not in ordinary matter.
It's a
in
very
ordinary
different
matter,
case.
we don't have that kind of breaking. That's a big problem in the stellar, star formation, because the angular momentum cause, resist the collapse. Anyway, thank you.
Yeah. Yes, absolutely. Yeah, I think that's very interesting. If the simulation is correct, and I assume it is, then these systems would be much simpler than ordinary matter. But it's a good question. Thank you.
Okay, is there any question?
I'd like to make some points clear. So for the instability, you say the Axion decay constant has to be close to the Gauss scale or Planck scale. So does it mean that the usual QCD axion in the QCD axion window cannot explode.
Okay, yeah. So maybe I was not clear enough. So for low decay constants, the usual story is correct, which is to say dilute Axion stars. So for example, the red curve here, right? Dilute Axion stars could grow in mass up to the critical mass, at which point they would collapse basically straight down in the figure and explode, right? So that's the prediction for low decay constants. When the decay constant is too high, let's say about 10 to the 17 GeV, like the brown curve, then if an Axion star tries to grow along this curve, it never reaches the maximum mass. It first runs into a decay instability. So what would happen here, we think, is that when the Axion star tries to grow in mass by a little bit, there are decay processes that burn off the extra axions. They quickly convert those new axions into relativistic particles that escape. So you would probably see a buildup of Axion stars sort of close to the border here. In that case, because they never reach the critical mass, they can't ever collapse and explode. So large decay constants don't explode. So that's also what's shown here. So there are no Bose-Novi for large decay constants, which means for the usual QCD axion, you have this whole collapse and explosion case is relevant.
So then the produced axion, the energy spectrum is around the axion mass, or what is the expected spectrum of the produced axion?
For the collapsing axion stars, or
collapse.
So that is given here. So this is the output of the simulation. So they have the collapse and they have a rapid emission of relativistic particles with a spectrum like this. So some of the axions in their simulation stay non-relativistic here on the left, but a large fraction of them come out relativistic with momenta greater than m. So our signal is coming from basically the first relativistic peak here with momentum of order 2 or 3 times m. Yeah.
My final question, then what is the characteristic signal that can discriminate this from non-relativistic axion dark matter?
Good. So firstly, as I mentioned, whereas the cold dark matter signal for axions would be very narrow, right? The energy deposited in the experiment will be of order m, right? Or the frequency of the signal will be of order m, or 2 pi m. Whereas our signal will be peaked at few times m, but it will also be broad. It'll be broadened not only by the intrinsic spread in the momentum from the burst, but also by this sort of wave spreading effect. So one way to distinguish it is that it will be a fairly broadly peaked signal as opposed to a very narrow signal that's extremely coherent with a very fixed frequency. We think that in order to make this really concrete, this is something we want to do in the future. To really nail down exactly what the signal will look like, you would need to include not only momenta in the first peak, but also these subsequent momentum peaks, so that maybe you could actually distinguish different self-interaction potentials potentially, because the peak structure will depend on the self-interactions. Working this out in detail is something we hope to do in the near future.
Thank you.
Okay, then let us thank speaker again. Thank you, Joshua. And we will have a 10-minute break and reconvene at 5:15 in Korean time. Okay, let's have a break. from Axion emission from supernovae and the latest developments. Pierluca, please start.
Okay, thanks for the introduction. Many thanks for this invitation to this nice workshop to discuss of our favorite particles. In this talk, I'll show you how to probe axion-like particles and axions with in astrophysical environments, especially with supernovae. Given the title of this workshop, I don't think that an introduction to axion is necessary, but this slide is only to summarize that axions were introduced to solve the strong CP problem, but then soon people realized that they are very good dark matter candidates, and so the interest toward axions grows and grows, and then it grows even more with the understanding that axions are a simple prediction of many ultraviolet completion of the standard model. So it's extremely interesting in this period to study axions, because as you see, the parameter space of axions is being filled by many different experiments with different, with the very interdisciplinary researches, and it's always interesting. So now in this talk, I will discuss with you about supernova axions mostly, because axions are weakly interacting particles, and so it's very hard to produce them in our laboratory experiments. And for this reason, we have natural factories, which are supernovae, a very extreme environment in which axions are copiously produced, and so we can probe efficiently them. A supernova is the final stage of a massive star. A star, during its life, burns lighter elements to produce heavier and heavier element, releasing energy which contrasts the gravitational collapse. But at some point, the star has burned all the lighter elements, and so only the iron core is present. But iron is the most stable nucleus, so it cannot be burnt anymore. And then there is no more radiation pressure to contrast the collapse. So the outer layers start to collapse onto the core, shrinking the core to very high density, to the nuclear density, the density of nuclear matter. And so at this point, the nuclear matter becomes very hard to compress, and the outer envelope bounces back in the so-called supernova explosion. This is a very naive picture of a supernova explosion, but it's enough to explain why this environment is so extreme. In fact, in this environment, the density of the matter in the core is around and higher than the nuclear density. So the orders of magnitude are 10 to the 14 gram per centimeter cube. The temperature of the supernova core is the highest, maybe it's the highest place in the universe, not as this place here, because this temperature is in the supernova core is 1,000 times larger than the hottest place in the universe, as Google says. And not only, some supernovae, the so-called hypernovae, host also a very strong magnetic field that we cannot even imagine in laboratory experiments. So this extreme environment is perfect for extremely low interacting particles. What we know about the supernova? The only supernova that we studied with our detectors, the only galactic supernova, and so it's closer and it's better known, was supernova 1987A. This supernova emitted its energy in form of a neutrino burst. From this neutrino burst, we detected only these dozen, a bit more than a dozen of events with these two detectors, Kamiokande 2 and IMB. These events are the result of this process, the inverse beta decay, the absorption of antineutrinos onto protons to produce positrons. So this is what you see here, the energy of the positron as function of the time. The duration of this burst is around 10 seconds in agreement with the standard expectation about any standard core collapse supernova. So at this point, only with this data, we can say that the standard model without any exotic particle explain this data, this sparse data. But if there are non-standard particles produced in a supernova, these particles are very weakly interacting, and so they escape from the core. When they are produced, they directly escape, draining energy from the core of the star, and so the energy budget for the neutrino burst is diminished in this way. And for this reason, the duration of the neutrino burst is strongly affected if the axion luminosity, so the energy emitted per unit time, is comparable to the standard losses. So this magic number that will be recurrent in next studies, because we want to calculate the axion luminosity imposing that it's smaller than the neutrino one. This is the energy loss argument, one of the most efficient methods to indirectly probe axions from supernovae. And so this is the picture of what we can do with the supernova. In this presentation, I will discuss all of these possible combination between production and searches. In this first part, I will focus on the production and then axions escape. So we don't see any of these signatures, but in any case, we can draw some conclusions about axions. Okay, so let's see what happens for the most simple naive axion model, QCD axion, coupled so with nucleons very strongly. And in a supernova, axions coupled with nucleons are produced by this process, the nucleon-nucleon Bremsstrahlung, in which two nucleons scatter by exchanging a pion or other mediators as a Rho meson, these nuclear mediators, and one of them emits an axion. This process is not easy to study because in this calculation, we have to include detailed nuclear physics for these interaction and also many bad effects because of the very high density of this environment. But it can be done, and this is the result of calculating the luminosity of axions emitted by this process. Skipping all the boring calculation, the result is shown here as a function, as a luminosity of the axions over the neutrino luminosity, as a function of the coupling with the nucleon and the proton, which is assumed the same in this case. This is calculated for a supernova model at 1 second. This is the benchmark time for which we fix our constraint on the energy loss. So we require that this ratio is smaller than 1 to affect not too much the supernova evolution. So in this case, we can exclude all the cases in which for which this ratio is bigger than 1. So all this range of couplings between 10 to the minus 9 and 10 to the minus 5. You see on the left part where the coupling is small, the axion luminosity increases as the square of the coupling, which is what we expect. In the other part, the luminosity decreases because axions start to be trapped into the supernova because of their strong interaction, so they don't drain anymore efficiently the energy. The very old and the first estimate for with this process were done with the OP approximation, in which the two nucleons exchange a massless pion, and the result of this calculation is the dashed line. But including, as I said before, the detailed nuclear physics and many bad effects, we studied that the emissivity is around 10 times smaller. So you see the result is the solid line, which is a bit smaller here, and this interaction is weaker, so the trapping regime starts later, because axion later, a higher coupling starts to interact strongly with matter. All these windows so is excluded by the so-called supernova bound. And to fix ideas with some model, real axion model, for example, with the KSVZ model, you see the bound on the mass. For example, in the OP, so the standard old calculation, this bound was 6 MeV, and we relaxed it with our refined calculation to 15 MeV because of the lower emissivity. For the DFC axion, which is also interesting for the observation of the future experiment IAXO, you see that the supernova bound reaches 10 MeV here, and this bound is slightly weaker than the perspective of IAXO. So it's interesting that the supernova bound is not excluding this experiment, and this experiment is complementary to the supernova bound. In any case, it's interesting to have different searches in the same region of the parameter space. Okay, so this is the simpler picture for hadronic axions produced in a supernova. But at some point, we realized that this is not, the nuclear bremsstrahlung is not the only process for the axion production in a supernova core. Actually, it was realized also many years ago in literature, where it was discussed that this process, the pion conversion into an axion, you see that here the coupling is with nucleons, even if there is a pion in the story. But this process is simpler than the process before, and it was found that it's the dominant axion production mechanism if the pion density is comparable with the nuclear density. But actually, nobody knows the pion abundance, and from very simple thermodynamics arguments, one can expect that this suppression, this population is very suppressed, because the pion mass is 135 MeV, and the temperature in supernova is around 30 MeV. However, in this recent work of Bryce Ford and Sanjay Reddy, they calculated the pion abundance for a dense supernova, for a dense nuclear matter. This pion abundance is the sum of two terms: the very small and negligible thermal abundance, as we expect, plus a term which is introduced by the interactions, because interaction between pions and nucleons reduce the energy cost for introducing a pion in the thermal bath. So only in this case, accounting for these interactions, we can have a not negligible pion abundance, which is around 1% of the nuclear matter. This abundance seems small, but in any case, we try to do this calculation with the right abundance, and this process is the leading axion production process in a supernova. The luminosity of this process is a few times larger or comparable with the nuclear bremsstrahlung case. So it's interesting that this process, always neglected before, now it's the most important process. And you see here in these supernova simulations that we run, including for the first time consistently pions and axions coupled with nucleons, you see that we reproduce the bremsstrahlung flux, which is a thermal flux peaked at 3 times the temperature. This is the peak energy, compared with the pion conversion flux, which is very non-thermal, because the pion energy, which includes also the pion mass, is completely transferred to the axion energy. So we cannot have axions with an energy smaller than the pion mass. This is the reason for this strongly non-thermal spectrum, which is extremely interesting also because this is a completely different signature from the bremsstrahlung case. Or now, the supernova bound becomes 2 times stronger than before, as you see in this table, including the pion conversion, because we are adding another axion production mechanism. So the luminosity is increasing, and we need a lower coupling to avoid a destruction of the supernova signal. But not only, the most interesting signature is for a direct detection of axions in a Cherenkov detector from a galactic supernova. We estimated that this process, which is the inverse process for the axion absorption, this process will produce 1,000 of events from a supernova at 1 kiloparsec. And it's interesting because this event will be at very high energies, where the neutrino background is vanishing, is very small, and so it's a clear signature. But we need more studies to understand especially this part of the interaction in which axions is absorbed, producing this delta resonance. All this process is not easy to understand, and so we are working on it. Now, always remaining with the supernova cooling bound, but let's consider axion coupled with photons. Axions coupled with the photons in a supernova are produced by the classical Primakov process, in which a photon converts into electrostatic field of an ion, and by, for very high masses of the axion, by inverse decay, in which 2 real photons merge to produce an axion. These 2 processes contribute in different regions of the parameter space. The Primakov is more important to lower masses, and the inverse decay at higher masses, responsible for this part of the bound. And imposing that the axion luminosity, again, is smaller than the neutrino 1 at 1 second, we obtain this violet bound here, for which excludes smaller couplings in the first streaming region, where axions are produced and they escape, and higher couplings due to the trapping, as he explained before, in which axions are reabsorbed in the same matter, and so they don't drain energy efficiently. As you see, this bound is interesting because it's complementary with laboratory researches from beam dump experiments for very high masses of the axions, and also with the HP bound here in this region. So this is an interesting complementarity with other bounds. Not only axions in this case, they could also decay inside the supernova behind the supernova shock wave, possibly revitalizing or helping the supernova explosion. In any case, we can only say that without a simulation, because we don't have a simulation with this process, we can only say that this process could modify the supernova explosion, because this is a part at zoom of the parameter space around this region here, in which this part is excluded by the bound. And here, as you see, inside the red line, the energy deposited by axion is comparable to the neutrino energy. So it's comparable to the standard mechanism for depositing energy in the shock wave. So maybe there could be with an effect of axions also on the supernova explosion, on the very mechanism of the supernova explosion, which is quite interesting to analyze with the more detailed supernova simulations. Not only axions, if they are coupled with photons, and if the supernova hosts a very strong magnetic field, they could also be resonantly produced by the photon-half conversion. So it's a process similar to the Primakov, but the external field is a magnetic field, the magnetic field of the supernova. And this process produces this blue line. The blue lines are produced by for plasmon conversion, so a photon converting into an axion. And this process is very different from the standard Primakov, from the expected Primakov phase signal, because the energies are lower. And for this reason, we have different signatures. And the most interesting signature in this case is, now we are producing by a process coupling with the photons the axion, and then it's heavy axions, and so they decay into a couple of photons, which reach our detector, and so we see a gamma ray signal from the axion decay. This gamma ray signal can be estimated with the blue line for a standard axion, heavy axions without a magnetic field. And you see that there is a peak of the gamma ray flux around a couple of days after the supernova explosion for the fixed parameters that we use for this figure here, just to fix the ideas. But if there is also a magnetic field in supernova, so we expect that this flux is very different because of the slower axions, and so they reach our detector later as gamma rays. And so we expect a larger peak, a larger flux, because there are more axions, and at later time, around 5 days after. If we detect, this is an estimate with the Fermi-lat. So in principle, if we see a galactic supernova with Fermi-lat and we see this signature, so in this case, we know that in a supernova there is a magnetic field, and we can also calculate by this mechanism what is magnetic field. So we prove the existence of ALPS first of all, and most importantly, we fix also the ALP mass, because this process is only efficient if the axion mass is comparable, is of the same order of the plasma frequency. So we very narrow the range for axion masses. And it's extremely interesting. Now, what else could happen if axions are also coupled with the electrons? Now, the production mechanisms are different. Now I'm considering that they are only coupled with electrons, which is another possibility. And so axions are produced by the electron bremsstrahlung, electron scattering with electrostatic ions, the electrostatic field of ions, and then the axion is emitted by the final electron. Not only, there is also a similar process to the photon coalescence, to the photon fusion, which is the electron-positron fusion. This process is similar, and it's, again, this process is important for higher axion masses. Now, the only difficult point in this calculation is that electrons in a very strongly interacting plasma, as the plasma in a supernova, are different from the standard electrons outside in the vacuum. So their mass, when they are in a thermal bath, their mass grow up to order of 10 MeV, and they also have an additional particle propagating in the plasma, which is called plasmino. And so for this calculation, in principle, we should take into account also the same processes here, but with the plasminos instead of electrons. But in this paper, I calculated that the plasmino contribution is negligible to these processes, and one can do this calculation only modifying the electron mass to this thermal value, which is very different compared to the vacuum value. The result of this bound is shown in this black region here. This is the supernova bound compared with other experimental bounds on low mass axions or from beam dump experiments which probe higher masses. And you see that the supernova bound also in this case is comparable with and complementary to the other experiments. And it's very important because we are going to lower couplings compared to the beam dumps. Okay, now you see that you recognize the classical feature of a supernova bound with the free streaming in this region and trapping in the upper part, as we discussed for the other bounds. Now, let's try to see some direct signatures from axions instead of only indirect signatures that we are mainly focused on now. For direct signatures, we can produce axions by one of these processes, or for example, by the nucleon bremsstrahlung. And if axions are coupled with photons, and they are light enough, they could convert into photons in the galactic magnetic field. So giving a gamma ray flux in coincidence with the supernova explosion. This is just an example of what could happen in this case. And having this signature in mind, we tried to calculate what is the diffuse supernova axion flux, which is the sum of all the axion fluxes produced by all the past core collapse supernovae, which is a very similar phenomenon to the neutrino, to the diffuse neutrino flux. And you see, this is the neutrino flux for comparison, which is at lower energies because neutrinos are more strongly interacting, so their energies are lower. And compared with the diffuse axion flux produced by a coupling with nucleons, which is less constrained, and so this flux can be at most large as this one, this line, or axions produced by their coupling with photons. So we have a Primakov production of light axions, and the flux is smaller because there are tight constraints on the GA gamma coupling. With these two fluxes, we can now try to construct our gamma ray signal, because there are two possibilities. If we look to our galaxy, we have our magnetic field there. And so this is a scheme up of the conversion probability of axions into photons. So our signal would follow the morphology of this scheme up. Now we can focus on a single source, for example, from supernova 1987A, which is this white dot here. And or in alternative, we can also see the diffuse signal. So let's focus for a moment on the supernova 1987A. So after the explosion of the supernova, we expect, if there are axions coupled with photons, we expect a gamma ray flux, which is not measured by the solar maximum emission, or better, this experiment, which was working at the time of the supernova explosion, measured only 0.6 photons per centimeter squared during the first 200 seconds after the supernova explosion. So with this number, we can constrain the axion to photon coupling. And for example, but it works only for light axions because they have to convert in the galaxy. If they are too massive, they don't convert anymore. But in any case, this bound gives if they're coupled only with photons, gives this bound, which agrees with the literature. I mean, I try to recalculate it, but it agrees with literature. And if we add also the nucleon coupling, this bound becomes 3 orders of magnitude stronger because the flux is larger, and so this bound is greatly enhanced. And this is only looking at the supernova 1987A, but there could be that this experiment was not working well or was not pointing to the right direction. There could be loopholes in this discussion. So to avoid loopholes, one could use the experiment now as a Fermi-lat to probe the diffuse flux. So now we have this diffuse axion background, which is converting in a diffuse gamma ray signal, which is measured by Fermi-lat. The standard gamma ray background is measured by Fermi-lat, and this is this red line as a function of the energy. And so we require that our non-standard axion production axion flux is below this line, which is a very conservative bound because we are not taking into account for all the standard and recognized axion photon production mechanisms. So in this case, we obtain bounds of this order of magnitude. In any case, you see that the strongest coupling is obtained in the case of nucleon coupling. This is an overview plot where I show the diffuse flux for the coupling only with photons, which is slightly stronger than cast. In any case, it's a different kind of searches in the same region, so it's always good. And a stronger bound is obtained with the observation of only the supernova 1987A because it's a pointwise source, so it's easier to study, and the bound is typically stronger. And if we add the nucleon coupling, you see that the diffuse bound increases a lot, becoming very strong, and also excluding part of these int of axion-like particles from neutron stars. And it's incredibly strong, also the bound from the pointwise supernova. Now we can do something better. So we can try to study the diffuse flux with Fermi-lat, but accounting really for the real photon fluxes and for the morphology, because before I studied only an average flux. So now we can account for all the morphology of the signal. And indeed, this is the signal measured by Fermi-lat in gamma rays. This is the sky map. As you see, this sky map is completely different from the expected ALP signal. So there is a very high probability that we can do a good analysis and have a very strong bound on the axion coupling. And this is what we have done in this paper, which is quite recent. And now the bound that we obtain, and most importantly, the uncertainty band, is shown here in this pink band. The bound before, only taking in account for the average signal, is this dashed line. So we've improved the bound, and not only we have added the uncertainty on the diffuse axion spectrum, because there is a difference if we include different kind of supernovae and with different probability of these supernovae. So we have uncertainty on this side and also on the magnetic field modeling. And all these uncertainties sum up to give this uncertainty band. So we have a bound which is now significantly stronger than cast in this region. Okay. And now let's try to do something different to probe, because with supernovae now we know that we can do a lot. We can probe a lot of different couplings and a lot of different axion masses. Now let's try to study with the diffuse flux, also AV axions. Now, what happens is that axions produce gamma rays, but no more for this conversion, because they are too heavy to convert efficiently. Now they decay into photons. So we see again a different axion gamma ray flux at lower energies, because now the energy of the axion is divided for the two photons. And this gamma ray flux is in the region probed by Comptel and Fermi-Lat experiments. In this case, we need both the experiments because we are at the edge of the two. So here you see the comparison between, again, an average axion-induced flux with the measured flux, and requiring that this flux is smaller than the observed one, we obtain tight constraints for very high masses of the axion. And in fact, here you see the brown region is the exclusion region for axions coupled only with photons. This bound is a bit stronger than the HB cooling bound, and it covers a region that is not covered by the supernova bound into decays. But the interesting observation is with a nucleon coupling, because this nucleon coupling leaves a very strong bound, in the maximal case of nucleon coupling, a very strong bound on G gamma, which is the strongest bound known now in this region. Now we have to be careful, because if axions also interact with the electrons, at some point after 1 MeV of mass, axions could decay into electron-positron pairs, reducing so the flux of gamma rays due to a smaller branching ratio. And this reduction is very significant. In fact, if axions have a very small coupling, as you see here, 10 to the minus 18, 17, with electrons, they soon could spoil this bound for this region above 1 MeV. However, axions, if they really are decaying into E plus, E minus, we don't know if they could give a signature. Probably they could, because positrons, the positrons produced in this decay, in this axion decay, are not invisible to our experiments. Indeed, positrons lose energy in the galaxy on a typical scale of 10 to the 3, 10 to the 6 years, depending on the density of the electron in the environment. And it's very likely that positrons lose a lot of their energy in Bremsstrahlung processes with the electrons in the plasma. And then when they arrive at rest, or close to be at rest, they annihilate with the electrons in the environment. And there are two different possibilities. One is that E plus and E minus, they annihilate directly, but this is a very suppressed process, because the most probable process is that they form parapositronium, so this bound state of E plus, E minus, and after some time, a very short time, they decay into photons. And they could, given the spin of this parapositronium, there are two possibilities. In the 25% of cases, E plus, E minus annihilate in only 2 photons, giving a monochromatic line with the energy which is the same of the electron and positron masses. But there is also a long-lived state, which is the orthopositronium. And in this case, the two spins are parallel. So to decay and to save all the quantum numbers, we have to produce 3 photons, which are not contributing to this line, but to the continuum, to a continuum spectrum. So now the question is, forget about this orthopositronium and consider only the parapositronium decays. Is it possible to explain at least a fraction of the 511 keV line with ALPS? The 511 keV line is a photon flux observed from the galactic plane, which is focused at energies of 511 keV. This question is interesting by itself, because there are not many theoretical models that can explain the complete signal, the observed signal. In fact, we observe signal from the center of our galaxy, but also from other galaxies, as you see in this plot here. So there are no theoretical models to explain completely this flux. Maybe axions could help, and this is the question. We try to address this question by calculating the sky map for the axion decay, because axions are emitted by the supernova, and then they decay into E plus and D minus, and then D plus annihilate, producing a photon. And if their coupling, the axion to electron coupling, is very high, then axions decay close to their supernova. And in this case, the signal that we observe is comparable, follows the morphology of the supernova distribution. But it could be that their coupling, the axion coupling, is very small, so they travel along before decaying, and the axion the photon signal is a smeared distribution of the supernova parent, of the parent supernovae. So this signal is completely different, is larger, especially in the vertical direction. And now let's try to see if what is the agreement between the SPI data, this is an experiment measuring the 511 keV line, as a function of the galactic latitude or longitude. Now let's try to see that if we can explain these red points, or at least a part of this flux, with axions strongly or weakly interacting with electrons. As you see, the weakly interacting axions have a smeared distribution, as we expected, and there is a quite good agreement in this vertical direction distribution. However, there is a very bad agreement in the horizontal distribution. So we cannot explain the 511 keV line with axions, unfortunately, but we can put strong bounds on these axions. And this observation, since axions follow the morphology of the supernovae, suggests that no core collapse supernova-based mechanism could explain the 511 keV line, given the geometry of the system. So the bound here is shown as in this red region, the exclusion, for different masses. This is in this plane GAE, GFP, electron and proton, considering because they are produced in supernova by Bremsstrahlung with protons. So this is the exclusion plot, which covers many orders of magnitude. But not only, we can only probe in another way this parameter space, because positrons produced by other galaxies, the same process happens also in other galaxies. So if axions are very long-lived, they leave the galaxy and decay into the intergalactic medium, in which there is a magnetic field that is small, but enough to trap positrons, which then decay, annihilate, producing photons in the intergalactic medium. And then these photons reach us, but they are reshifted. And this process gives no more rise to a monochromatic line, but to a continuum continuum signal, which is this black line here. You see it starts at 511 keV and it's peaked for the maximum supernova redshift of the supernovae, which is around 2. So we have the energy of photons in this expansion in the universe. And this flux, compared to the experiment EAO and SMM, which probe this X-ray region, gives a stringent bound on very low, very small coupling of the axion with electrons. And this is the reason why we exclude also the blue region here. So it's interesting that we are covering 10 orders of magnitude with this idea. Now, so I arrived at my conclusion. Maybe I went a bit fast, but I said a lot, and everything points to the importance of axions from supernovae. And so we are all waiting for the next supernova explosion, but it seems that UFOs are more ordinary than supernovae. So let's wait and hope. Thank you for your attention.
Thank you for the nice talk with diverse axion couplings in supernovae. Let us have a Q&A session then. Is there any question from audience? Let me first ask a question. So, understanding supernova has a long history, as far as I know, but we use the old arguments like Raphael criterion. However, even now, the development in theory and simulations are still ongoing for supernova, as far as I know. So, is there any development or new feature like as you mentioned, the pion abundance is newly investigated? I mean, understanding is reconsidered, and the axion emission rate is quite hugely modified. And is there any this kind of thing happens in supernova theory?
Okay, yes. What we are using actually is the old idea is to constrain axion or weakly interactive particles with supernovae with this criterion. But the new part is that in any case, we are understanding much better now the supernova explosion, and actually reaching the point in which we can also self-consistently explode supernova in 3 dimensions, which was because in 1 dimension they don't explode naturally. So on the astrophysical side, on the standard side of supernova mechanism, we are understanding much better, and everything is quite running in this direction. Now the question is, now that we understand better supernova, the standard supernova mechanism, how to constrain these particles. And this is a difficult question to address, because clearly, if we run a real supernova simulation and we compare in principle for each axion coupling, we should run the simulation obtaining the neutrino flux, the neutrino burst, comparing it with the expected signal in K2, for example, to compare with the supernova 1987A. But then at this point, one can have a different signal from the supernova because of the different equation of states, because of the different progenitors. So there are a lot of uncertainties, which are very difficult to put all together, because for each different uncertainty, in principle, you need to run a different supernova simulation. So it's very time demanding. And actually, we are trying to model also the neutrino signal to extrapolate from the supernova, from different supernovae simulations, the neutrino signal. In principle, one could say, can we produce a synthetic neutrino signal also without running a simulation? And this is interesting. It would be extremely useful for the axion purpose, but it's still very hard. It's just an idea now. It's at very beginning, so it's completely hard to do this.
Oh, okay, yeah. So do you expect any this kind of dedicated simulation doesn't change the order of this argument? Like neutrino luminosity doesn't change change a little bit by a factor of few, but not change it by an order of magnitude, right?
If we continue to explore the supernova 1987A signal, yes. I think that there could be not a big difference on this magic number here. But with the next supernova, we hope to see also more neutrino events. So to reconstruct better all the signal. And in that case, you would have a very strong and probably more very tight constraint on these exotic values. So probably in 30 years now, we can say that the axion luminosity must be smaller than the neutrino luminosity divided by 10 or by 100. Yeah. But in any case, also here, we need to understand all the uncertainties related with our supernova modeling.
I see. Thank you. Thank you very much. Is there any question?
I have a small question. So maybe in page 36, we mentioned some gamma ray, the constraints on the action photon coupling from the gamma ray flux observations. Maybe I just missed, I think I missed this point, but why does the bound on the GA gamma depend on the value of GAP, the action proton coupling?
Okay, because we are producing with the protons, with the Bremsstrahlung.
Okay.
So in the first case here, in the first line, you are only producing with Primakov. And so we have a smaller flux, so a smaller, weaker coupling, with a weaker bound. But then here, if we add also another production mechanism, which is much more efficient than the Primakov conversion, because this coupling could be higher than this one, basically. And so we have a higher component at the production, and then a stronger bound for this reason.
I see.
Yeah, because we produce more. So if we convert the same quantity, we have a stronger flux of photons.
I see.
Related to his question, I want to ask that what kind of value for GA and neutron coupling is assumed in this case?
No, in this case, it's assumed to be 0 because, for the KSVZ model, it's very compatible with 0, but it's just a model. It's extremely model independent. The difference shouldn't be huge because we are saturating the supernova bound with this value. If I add also GAN, for example, I have to lower this coupling, but at the end, the axial luminosity is the same. So this bound is at the end is unchanged.
I see.
I have one more question, maybe in page 40. Yeah, so this is the morphology of the gamma ray signal. Is it correct?
Yes, the expected gamma ray signal from Axion conversions. Yeah.
So does it depend much on the assumed modeling for the galactic magnetic field? The constraint on the GA gamma itself. I'm just curious. Yeah.
Yes, it depends on the galactic modeling, and this is the reason for this band also. But this dependence is not extremely strong because in the analysis, we selected the right windows, the most model independent windows to study this flux, and also the most suitable windows to have a smaller, to have a better understanding of the standard signal, And so putting all together, if you run the right analysis, you could have a small impact or a relatively small, this impact of the galactic modeling on your signal, even if it's quite counterintuitive, because I know that some galactic field models could produce a smaller flux in these off-plane regions. But for example, if we look at this region, it's quite model independent, or at this one. So this is the main reason.
I see. Thank you very much.
Okay, is there any question? If not, okay, then let us thank speaker again. Thank you, Pierluca.
Thank you, it's a pleasure.
Yeah, it is our pleasure. And this is the end of the second day of the workshop, and tomorrow is the last day of the workshop. The talks will be given following the same schedule as today. Then, okay, then let us see you all tomorrow.